So I have prepared a CAD file which includes all geometries within it, but you can also import all of them separately. Now, first CENOS asks me if I do want to make automatic cross-section cuts for my coils. So this is actually the simulation setup, geometry setup that you see. We have two wireless charging transmitter coils and one receiver coil. Now, for CENOS to be able to apply any kind of voltage or current or power input, we need cross-sections. I have not made them automatically, so CENOS will do it in, automatically in my place. So I click yes. Now the CADs are being sliced, and now I want to generate my air domain around the system. All right, now we need to assign roles to our geometry. Essentially, explain to CENOS what we have in our system. So I will start with my transmitter coil. So I actually have two. So I'm going to select the first one, and then I'm going to add another transmitter coil like this. I'm also going to select my receiver coil. Now, if any other geometries are in a way, I can simply make them transparent so that the selection happens more easily. And on top of this, I still have my ferrites. So in this case, both receiver and transmitter ferrites are made of the same material, so I don't really need to separate them, and I'm going to include them in one group together. So I'm going to select both ferrites and assign them. Now I need to set up the physics. Now we start by defining the general simulation control parameters. Now you can see that the physics are divided into different tabs, meaning that for each volume in your system, we have a separate tab to easily define physical parameters, physical properties of our parts. Now we start with the simulation control, and we are going to input an end time of 2 just to take a look at the transient analysis of the simulation. Now we are going to also input a frequency of 130 kilohertz, which is the operational frequency of which is within the operational frequency of most of the Qi standard wireless chargers for smartphones. And then I'm going to start to define transmitter coils. Now for transmitter coil definition, I need to enter the number of turns or strands. So basically how many strands in your leads wire you are going to have. Fill factor, which defines what kind of a shape or cross section you have for your strands. So most commonly used is circular one, which has a fill factor of approximately 0.785, but you can alter it depending on your geometry. And of course, some kind of a power, current, or voltage input. Now, for number of turns, for this kind of a transmitter coil, it is built with leads wire from 23.5 turns within this coil, which has 115 strands, in total resulting of around 2072 strands. And I'm going to apply a voltage or input voltage of 8 volts. Now, for the second coil, I'm going to input the exact same values because both of these coils are identical. And I'm going to input the same 8 volts. Now for my receiver coil, I don't need to define any inputs. I just need to define the same number of turns and fill factor. Now this kind of a receiver has 66 strand leads wire, which has actually 10 turns, and it has 2 layers of wired turned leads wire, which in total results of approximately 1,320 strands with the same fill factor because of the same geometry. Now, the last thing we need is to define the ferrite. So for wireless charging systems for smartphones, we usually use either manganese, zinc, and ferrite or something different. So we just select it from our material library, which I have it here with the latest used materials. And essentially, we're good to go. Now, if you do want to include any kind of additional simulations or modeling, for example, you can input also conductive surfaces or enable thermal analysis. You can do that as well by simply enabling this checkbox. But for this example case, we're not going to do that. Now the last thing we need to do is we need to come and we need to generate the mesh to take a look if CENOS generated mesh is fine enough to be used for our simulation purposes. So we just wait while CENOS generates the mesh file, and honestly it looks pretty good. So I don't think we're going to need to manually modify it, so we can simply go and click the Run Calculation button. Now, I have already pre-calculated the same case and calculated the results. So the calculation of such simulation takes approximately 5 to 10 minutes, and the end result looks like this. Now, I have tweaked the results a bit, but essentially from the CENOS Wireless Charging simulation software, you can get this kind of results. So we can visualize a lot of different things. So we have very beautiful three-dimensional results. So on the right side, you can see we can analyze the magnetic flux density within the coils, so we can see how they behave. We can also analyze the casing itself, so sorry, not the casing, but in this case the ferrite shielding, which we can see here on the left side. So here we have visualized loss distribution, and actually we can disable the visibility of some of the coils like this and show only the transmitter ferrite. So we can actually very deep, in a very sharp detail, see the loss distribution, which essentially shows you the parts that are prone to heating. So if you do want to modify or improve your designs, this is the way on how to do this. In addition, you of course can visualize also electromagnetic field, as we saw initially visualized like this. So you can also evaluate manually how the electromagnetic field looks inside and around the system, and you can also see how strong it is, and well, yeah, if the shielding works or not, and if this magnetic field affects anything in the vicinity of the system. Now, on top of this, we also have the numerical parts of the results, which are called time charts, where you can find a couple of characteristic values that defines your system. So we can we see mutual inductance and total losses of the system, which are in watts in this case. We see the coupling coefficients, which are approximately 0.3, which is not very bad, but it definitely could be better, which essentially defines how efficient your system is. And also we can see the quality factor of separate coils. So we can see that for transmitter coils, the quality factor is pretty high, but for receiver coils, we might be looking at some improvements. And that is the end of our walkthrough today. Thanks for watching, and see you next time.